So today we are very fortunate to have an esteemed physicist, Linde, who's going to speak to us about the universe or multiverses. He was born in Moscow and studied physics at Moscow State University. He did his graduate work at the Linde Physical Institute. He's also worked at CERN, and he became a professor of physics at Stanford University in 1990. He is the author of 2 books as well as numerous journal articles, and he's received a variety of prizes from the academic community for his work in physics. So it's my pleasure to welcome Linde today. Thank you.
Thank you. Okay, it's my privilege to give a talk at SETI Institute, which was, well, specially developed for study of things which are kind of related to what I'm going to talk about. Mostly, the subject which I am going to cover will be related to the developments in something which is called inflationary cosmology. This theory was invented about 30 years ago. And one of the consequences of this theory was the idea that our universe may be divided into huge parts with different properties. So essentially the universe becomes a multiverse. But somehow the idea was proposed about 30 years ago, and it became popular only recently. So I will try to explain the nature of the idea and also the reason why it was not popular a long time ago and why people start being interested in it starting approximately 10 years ago. So historically, the question was quite opposite. It was why universe? Why the universe is everywhere the same? Because uniformity of our world. Why it is so that when we look to the right and we look to the left and the universe seem to us the same. That's why it was called universe. In fact, it was a basis of something which is which was called cosmological principle. The universe must be uniform because, well, because of the cosmological principle. So sometimes I used to make a joke that some people who do not have good ideas, they have principles. But then I learned that this principle was invented by Newton and Albert Einstein, and I stopped making this joke. Well, so let's see. I mentioned inflationary theory, and I will try to explain what is going on. So inflationary theory, the basic thing is that it explains why the universe looks uniform at the scale which is accessible to the present observations. But surprisingly, the same theory which explains the uniformity, this theory predicts that the universe is expected to be 100% non-uniform at large scales, and it actually looks very, very interesting. It looks like a huge, eternally growing fractal. Okay, so that is something which I'm going to explain. But first, some basic things. Some basic things about the Big Bang story. So this is the graph which was, well, in all textbooks for, I don't know, maybe 40, 50 years, at least these 3 low lines of it. So the idea was that the universe can be closed, open, or flat. It's not very easy to explain meaning of it because these words imply using of, well, Riemann geometry, non-Minkowski, non-flat space, something more complicated, curved space. So we can use these words only by, well, explain them by analogies, unless we really want to go to general theory of relativity, and then it will spoil your appetite, I'm sure. So here, analogy. If you have a flat table, okay, and you send 2 beams of light, 2 parallel lines, then these parallel lines on the flat table, they continue going, they will never intersect, and they will never diverge. They will be all the time at the same distance, okay? Now, you go to equator, and you send two parallel lines toward the North Pole. And near equator, these two parallel lines, they will be parallel, but then they go. Okay, so they meet. This is something which is similar to geometry of a closed universe. So if the universe is closed in the sense which requires general theory of relativity to explain, but the idea is that it looks like it is a surface of a huge spherically symmetric cosmic balloon, and if you send two parallel beams of light, then they meet at this North Pole and again at the South Pole, but near equator they look parallel. Okay? Now, if, however, you just imagine a hyperboloid, which is the thing which appears when you have a hyperbola and you start rotating it, so you have some surface like that. Then you send two parallel lines near the equator, and they continue diverging at infinity. So these are three different geometries. Either the parallel lines remains parallel, or they converge, or they diverge. And there was a saying among cosmologists that geometry is destiny. This is very deep thought, which, well, deep does not mean necessarily right, but it was, if the universe is closed, so it has geometry similar to the geometry of a surface of a globe, then it's doomed to collapse. Because what means closed, this means that it's so heavy that even light trying to go outside, it falls back on it. And the universe itself, when it's expanding, it falls back on itself and it dies. So this is this yellow curve. It starts expanding. This is something like size of the universe, which is not a very good word for describing it, because if the universe is infinite, what do you call by size? But if you have even an infinite universe, you can put two black marks on two points of it, like two galaxies. And then the universe expands, you say scale of the universe growing. When it contracts, you say scale of the universe is decreasing. So this is scale. It's not necessarily the size, which may be infinite, but the scale of the universe. So the scale of a closed universe expands, and then it contracts. In fact, a closed universe is finite. So scale, size, you can use any of this. Now, the second model is a flat universe. So flat universe is the universe where parallel lines do not intersect. And it is not just the surface of a flat table, because what's going on, you send two beams of light, they continue being parallel to each other, but the universe expands. So they're parallel lines, but the universe stretches, okay? And it will continue expanding forever. Now, the third model is open universe, which is similar to the surface of the hyperboloid, and then it also continues expanding forever, just the geometry of space is not flat, okay? Now, what we learned, starting from 98, our universe is not empty. Our vacuum is actually heavy. It's energetic. And that is, well, one of the most magnificent discoveries in cosmology ever made. These guys, they measured vacuum energy. They measured energy of empty space, and they have proven that it's slightly positive, non-zero, tiny, tiny, tiny. That's why we don't think that there is anything in the vacuum. And this tiny energy is sufficient for starting a stage of exponential growth of our universe. This is very slow growth. It happens like once in 10 billion years, roughly speaking, our universe doubles in size. So we'll have lots of time to see how its size grows. But what does it mean? This means that even if the universe is closed, or flat, or open, it will obey later this rule of expansion. It will continue growing exponentially without end. Even closed universe will not collapse on itself. Geometry is no longer destiny. Okay? So you have just eternally expanding, exponentially growing universe. Once we see right now galaxies which surround us, well, approximately 100 billion years later, we will stop seeing any, because they will all run away. Okay? So that's a prediction. That is a prediction, but nastier predictions will come later. Okay? So not seeing galaxies eventually will be your smallest concern. Now, so this was stage of exponential expansion when the universe is old. But now the question was, how did it happen that our universe became so big to start with? And this is the other stage of exponential expansion, which is called inflation. And that is very, very, very rapid expansion when the universe was extremely young. And that is the main subject of my talk. So apparently there is this already discovered stage of exponential expansion, which nobody expected. Experimental discovery of 98, which during the last 14 years became better and better established. And then there is this stage of inflation, exponentially rapid expansion, in the beginning of the universe evolution. So we will concentrate mostly on that. Inflationary theory was invented in order to answer several different cosmological questions. And these questions were so metaphysical that in the beginning people really didn't care, because most of the people who asked these questions were pathologists. People knew that these are stupid people, they asked this question, just ignore them. So one of the questions was, what was before the Big Bang? Okay? So, well, I learned cosmology in Russia. We used the textbook by Landau and Lifshitz, Field Theory, and there Landau and Lifshitz, famous scientists, they explained that it does not make any sense to ask a question, what happened before the universe creation, because the solutions of Einstein equations cannot be analytically continued to the domain of negative time, period. But nevertheless, everybody asks, so where our universe came from? So it's a stupid question, but you cannot stop people thinking. Now, then, why is our universe so uniform? That is this principle of, cosmological principle. So why the universe is so uniform? It is on the large scale uniform. It is not uniform near us, okay? But on a very, very large scale, when you scale much larger than the size of the galaxies, the universe statistically is very uniform, better than 1 part in 10,000. So who polished the universe? And you may think, well, maybe it is not really a complicated question. Maybe you start with any kind of initial conditions, and then you solve Einstein equations, and then you get homogeneous universe like easily. Okay, so this question was analyzed by famous British scientist Stephen Hawking. You know this person who? Okay, so he studied it in '73, and together with his collaborator Collins, he have written a paper which ended up with the following mathematical formulation. Just bear with me, and I will translate it from English to English. So, on the set of all possible initial conditions, the set of those initial conditions which reproduce uniform homogeneous universes like ours has measure 0. Okay? So, translation, it's just impossible. If you want to start with any arbitrary initial conditions, get our universe, just forget about it. Okay, so that's translation. Now then, why then our universe is so uniform? And Stephen Hawking answered, it is uniform because if you start with generic initial conditions, the universe would be so non-uniform that we would be unable to live there. And therefore, our universe is uniform because if not, we would be dead and we would not ask stupid questions. This is called Entropic principle. It's very controversial, but very, very clever principle. What was not enough there is that actually it is not necessary for the universe to be globally uniform. What we need for our life is an order in the vicinity of a solar system. And who cares what is 10 billion light years away from us, okay? So Entropic principle is not enough to explain why the universe is uniform, so we are trying to understand it. Why the universe is isotropic, meaning why the universe is like a sphere rather than like a cucumber. Why all of its parts started expanding simultaneously. See, if, for example, the universe is infinite, this part and this part of the universe time equals 0, the universe starts expanding. Now, how this guy knew that this guy in his vicinity start expanding the universe? Because the knowledge about, well, the universe starting travels with the speed equals speed of light. So if there is like almost infinite distance between these two people, then they have no chance to start expansion simultaneously. So when I was a student, I was, well, I remember reading popular journals about the Big Bang theory, and I was thinking that when I'm growing older, I will go to the university and I will ask clever professors, so how actually it happens, who gave a signal, okay? And when I became a student, I came to professors, it appeared that they didn't know that the question exists. Now, why the universe is flat? Which means that parallel lines, nobody have seen them intersecting, okay? So our universe is almost exactly flat. Now we could think that maybe you start with curved universe, you start expanding, and longer you're expanding, the more flat the universe is, which is in fact totally opposite to what really happens if you solve Einstein equations. What happens is that in order to get the universe approximately flat, like, well, parallel lines diverge just a little, like 1%, when they fly through our universe now, okay? You must prepare the universe which would be flat with accuracy 10 to the degree minus 60. Okay, so it's just, again, impossible. This question, why the universe is flat, can be shown to be equivalent to another stupid question. Why there are so many people in this auditorium? Okay, no, I mean, you usually take this question as a fact of life. So we live in Palo Alto, and well, SETI is a famous institution, and many people are interested in cosmology. Some of them decided to come. But why there are so many people in Palo Alto? Actually, Palo Alto is a small city, and much more people in San Francisco, and lots of people on the Earth, and there are lots of people on the Earth because Earth is so big. Why Earth is so big? Well, actually, Earth is just one of the many planets. There are many other planets. There are many other stars. 10 to the degree 11, like 100 billion stars approximately in our galaxy. Why there are so many stars in the galaxy? Well, actually, there are 10 to the degree 11 or 12, so meaning 100 roughly billion galaxies in our part of the universe. Why there are so many galaxies in our part of the universe? And that because the universe is big. And why the universe is big? Because it's the universe. Okay? So, if we start studying this question carefully, really studying proper initial conditions, natural units of length, etc., the typical universe would contain one elementary particle, or maybe 10 elementary particles. Right now we see approximately 10 to the 88, it's like a billion, whatever, particles, many, in the universe. Okay, so it's really a physical question, why there are so many people in this auditorium, because typical auditorium in a generic universe would consist of only one elementary particles. Okay, so see, the questions look silly. If you study them a little bit, you find out that actually they are real questions. And then once you learn how to answer them, you cannot force yourself to forget about it. See, we learned how to answer some of them. We still do not know what was before the Big Bang. But for all other questions, we have a probable answer. Once we get this answer, we remember it. Now let me formulate one of these questions in a slightly different way. Energy in the Big Bang theory. Oh, okay. I guess I'm going much slower than I expected, but I hope that it does not subtract from your, interest to this story. If I cover 1/3 of the material and it will be clear, then it is the same as covering 100%. Now, the reason why I'm showing this slide is that once I was invited to some Nobel symposium on energy, and people from oil industry, whatever, they came to this Nobel symposium, and I was supposed to give a talk, the opening talk, and I thought, these people are crazy. I do not do oil. Okay, so and then I realized that actually I'm studying this energy thing, because matter is energy according to Einstein theory. Energy is mc squared for each of us. So where do we get all energy in the universe? And when I start, well, trying to interpret how can I tell these people where the energy came from, I realized that I should explain them that actually energy is not conserved in the expanding universe. Because, for example, when the universe is filled with gas of particles, and there is some pressure in it, and the universe looks like a big box, and then this gas of particles makes some work expanding the universe, so it loses some of its energy, and therefore the energy of the gas decreases when the universe is expanding. So the whole idea about energy conservation actually does make sense in expanding universe, but it is very weird sense. The total energy of matter plus the total energy of gravity is exactly equal to 0. Energy of gravitational interaction between particles in the universe, it's negative. And it's negative energy. You add it to this positive energy related to the mass, and you find out in a very tricky calculation that the sum of these two is 0. So energy is conserved, but it's just 0 start, 0 finish. We are interested in energy of matter, why energy of matter grows. And in this example, normal cosmology, the cosmology which we used to know, this is a standard hot Big Bang story, the universe is filled with hot gas. When the universe expands, energy decreases. So it must start with energy which was much larger than the total energy which we have right now. And if you translate it into, well, energy is mc squared, then it's possible to show that the initial energy of all matter in the universe at the beginning of the universe expansion was greater than 10 to the 80 kilogram, 10 to the 80, the billion of a billion of a billion of a billion of kilogram, or tons or grams, nobody cares. It was huge, okay? So how then you do it? And of course, the normal explanation was, well, who can make a big miracle? Yes. Okay, so it's only God gave you this universe together with this 10 to the 80 grams or tons, whatever. And then it polished the universe with this huge accuracy, like 1 in 10,000, make it totally spherical, and ignited. It's different. Causally disconnected parts which did not know, but God's eye just ignited okay. So this is not something which physicists would be very comfortable about. So they tried to do something better. And then what inflationary theory does, it solves many of the problems of the Big Bang theory and explains how you can get the whole universe from inflating of less than 1 milligram of matter. And who gave you 1 milligram of matter? That's a complicated question. but it is still much better than 10 to the 80 tons. Okay. Okay. Actually, we have some ideas about 1 milligram, but okay. So now let me give you one example of this inflationary theory. It will require to explaining something which people right now discovered at LHC accelerator in Geneva, scale field. One example of a scale field is this Higgs boson. So you have read in newspapers. They discovered Higgs particle, probably. Okay? So most probably they did. They do not say that we have discovered, but everybody knows that, yeah, probably they did. So one way or another, this is the scalar field. So the meaning of this scalar field, well, what is the meaning of electromagnetic field? Electromagnetic field, you have a field pointing in some direction, like magnetic field from the south to the north pole of the Earth. Scalar field is much easier. It's just a number which does not point anywhere. So if you have, well, magnetic field, you must think about it. It's number and also the direction. Scalar field, it's like electrostatic potential. So you have, for example, here 110 volts in a socket. Okay? So imagine that you have everywhere in this auditorium 110 volts. You do not have 0. Then you would not have current, you would not have lamp shining, you will just be a vacuum state, just 110 volts. That's it. For current to work, you need to have 110 and 0, then you have current. Okay? But 110 is just like vacuum state. Example. Have you ever seen these, well, high voltage electric lines, right? Okay. Have you seen birds sitting on this? Okay. They see they're quite comfortable there. Have you ever seen these birds with one leg on one line and another on another? Okay. They just got fired. They all evolutionary disappeared. Okay. Because this 10,000 volt, it's fine. But 10,000 and 0, that's not fine. Okay, so scalar field is something like that. It's not exactly this, but it's very, very similar. It's like a specific, almost vacuum-like state. So if you are surrounded by the scalar field, you would not even think that you're surrounded by it. Like if you have 110 volts, you cannot care less. Okay, at least birds don't. Now, according to this discovery which was made at CERN and the theories which were developed already more than 30 years ago, you are right now, and me too, we are all surrounded by a constant scalar field which is called Higgs field, classical field, which makes every particle in our body massive. Meaning, if you turn it off, you become light-like person. So every particle of your body will fly with a speed equal to speed of light. Non-stoppable. We would not be sitting in the chairs. The fact that you are sitting means that you are surrounded by the scalar field. According to the theory, for which many people already got their Nobel Prizes. Okay? It's not scary. Not painful. Moreover, you move from one point to another. And this is the same scalar field. It does not prevent you from moving. Meaning, scalar word means it's scalar with respect to the Lorentz transformations, which means that you turn like that, does not feel anything. You start running, do not feel anything. It's really like another vacuum state. So fields like that, they may play an important role in cosmology. And one difference between this field and these 110 volts in the socket, this 110 volts does not have any energy associated with it. Only when you have 110 and something else, then the difference between energies produce electric field and then it has energy. But just this number 110, no, it doesn't have any energy. But the scalar field might. Okay? So this is the simplest theory of a scalar field, where the energy of the scalar field is proportional to the square of its amplitude. Okay? So see, this is letter phi. This is picture from my old paper in Scientific American when it was published. Editors have thrown out this thing. They say no Greek, no Latin, okay, because the text of the paper must be understood by every dentist. And I thought, dentists usually know. but anyway, so this picture you will find there. So this is the value of the scalar field. This is its energy. And in the simplest case, it's quadratically dependent on the value of the scalar field. So what do we know which is quadratically dependent on the... I'm not going to solve these equations, don't worry. I'm going to point at them. Okay? So what do you know with the energy which quadratically depends on the value of something? Like if you have a pendulum, okay? So you deviate this pendulum, you take it off from the minimum. And the energy of the pendulum is approximately proportional to the square of the deviation. You take the spring, you stretch it from equilibrium by x. The energy will be proportional to x squared. So that's the simplest thing, which is called harmonic oscillator. So the energy of harmonic oscillator is proportional to the square of the deviation. This is Einstein equation, somewhat simplified. This is the scale factor of the universe. Dot means speed, velocity with which universe expands. This is the scale factor of the universe. Ratio of velocity to distance is called Hubble constant. Now, we used to think Hubble constant is something which astronomers go and measure. This is constant. Now, in general, it is not constant. In general, it depends. In early universe, it was much, much larger. Einstein equations say that the Hubble constant squared is proportional to the energy of the field, which is quadratically dependent on the value of the field. Okay? So that's a bit simplified Einstein equation. I've thrown out some terms which disappear themselves when the universe becomes sufficiently large. Now, this is equation for the scalar field itself. It looks a bit scary. There are all of these dots around. But this is the equation which is very familiar to everybody who studied mechanics. So x is deviation of harmonic oscillator from its equilibrium position. X dot is velocity with which it moves. X2 dots is acceleration. So the standard equation for harmonic oscillator is acceleration is proportional to minus deviation. So you deviate it, you accelerate back. Okay, acceleration is opposite to the deviation. I deviated it positively, acceleration is negative, returns your thing back. This is slightly unusual term. It is like if you put, well, your pendulum into a viscous liquid. And then it's like viscosity, which stops this pendulum from swinging back quickly. If viscosity is very large, then pendulum will move down very, very slowly. This is equation which is true, nothing is invented, for scalar field phi in expanding universe with expansion given by this Hubble constant. So this coefficient alpha in equation for harmonic oscillator is viscosity. In the universe, this Hubble expansion, speed of expansion of the universe, works like friction for the scalar field phi. So what does it mean? When scalar field phi is large, then Hubble constant is large. When Hubble constant is large, friction is large. When friction is large, scalar field moves down very, very slowly, like a ball in a viscous liquid. If it goes down very, very slowly, then for a long time, this field phi remains almost constant. And then I see equation. A dot divided by A is equal to constant. So that's the simplest equation of calculus you can ever imagine. If you have equation A dot divided by A approximately constant, and this happens when the scalar field phi is large, Hubble constant large, large friction, almost constant, then this is a solution of the equation. That's exponential expansion of the universe. It's a very, very simple piece of mathematical physics. It remains a miracle for me that this solution was discovered only 30 years ago for expanding universe, because it's so trivial, okay? But then you look at it, this is trivial. Why it was not discovered, I don't know. Okay, so we found it, and then let's see what does it mean. This means this. You start with tiny, tiny universe, and if this universe was filled with large scalar field, now, if it was filled with small scalar field, nothing like that happens. But if we consider a tiny piece where by chance, by whatever, you have large enough scalar field, then this part of the universe starts expanding exponentially. How large this exponential expansion is? In, well, the simplest model which I've just shown estimates gives you this number, that the typical universe expands by this number of times during inflation. So what does it mean? Well, let's say start with the universe size 1 millimeter. After expansion, it will be this 10 to the degree whatever millimeters, or meters, or kilometers. Really does not matter, because this number is so huge. And what does it mean? You start with tiny universe, whatever tiny size you want to start with. And then after that, it looks like enormously large balloon. You stay on the surface of the balloon, and you do not see its south and north pole. So you do not see parallel lines intersecting. You see the huge universe. That's why there are so many people. You see that if the universe was originally inhomogeneous, then all inhomogeneities are stretched. Like if you have the, well, Everest mountain on the Earth, and just imagine that our Earth just blows up by this amount of times, then the Everest mountain blows up this way, and therefore to go from the down place to the top of it, you will need to go this number of kilometers. Nobody does. So for every observer, the universe, the Earth, whatever, will look totally, absolutely uniform and homogeneous. So we know why the universe is uniform. We know why it is big. We know why it is flat. Okay? So it's just one simple thing. You have very rapid expansion. So to summarize, how does it look? You start with the universe, and because I came from Russia, I start with the red universe. Okay? Initial, very, very small size. You cannot go smaller than that because on the smaller scale, quantum fluctuations of space-time are so strong that the universe bends, your rulers bend, whatever. So started with something very, very small, and after a very quick stage of inflation, approximately 1 billionth of a billionth of a billionth of a second. Seriously, okay? The universe becomes like that, and I said, in any units of length. So it's big. So we solve this problem. But now then, the question is, why everything is colored red? We observe, we live here, and we observe this part of the universe. We do not observe this. So why don't we, yeah, okay, that's another story. It was just, I want to be, how to say, to be fair. Red was from Russia. This was black, okay? This was Henry Ford. Any customer have a car painted any color that he wants as long as it is black, okay? So it was just in our blood that everything must be uniform and we do whatever we want as long as it's uniform. Now, here comes the multiverse. So that's the simplest example. Instead of starting with a red ball, let's start with a football. Some part is white, some part of black. Let us paint it even. So you have some parts white, some part red, some part black, and then let it expand. So what happens then, this part becomes much larger than what we can see in the best telescope. This part becomes much larger. Any person who lives here will believe that the universe must be blue, because that's what he sees around. He will try to construct a theory which explains why the universe must be blue. It just cannot be red, because he does not see red. That's why we will try to explain why the universe must be red. That's what Einstein wanted. He wanted to explain why what we see right now is inevitable. That whatever choice God had, he used it all and he produced only one logical possibility. It was his hope. Okay? And then physicists, they were living with this hope that eventually we'll find that there was no other logical possibility to construct a consistent universe. You always end up with blue. But people who will live here or here, they will try to construct a universe saying that the universe must be red. And whatever is not red, then eventually will become red. Okay. So we do not see other points, other parts of the universe. So there are 2 points of view with respect to this theory. Because you may say that pessimist point of view. If each part of this multiverse is so large, we will never see its other parts, so it's impossible to prove that it's actually a multicolored universe, right? Okay? So the multiverse theory, unlike the universe theory, okay? The word saying that you cannot prove it. Optimist point of view. If each part of the universe is so large, we will never see it, so it's impossible to disprove that we live in the multiverse. Now, why I consider this second part more convincing? Because it's generic. Because you see so many different people in the auditorium. They are not just stamped from, actually they are stamped from the same material. It's water, it's carbon, it's all based on the theory of electromagnetic interactions, well, a little bit nuclear physics, that's all. So you may think that if you say magic words, nuclear physics plus electromagnetic interactions, maybe a little bit of weak interactions, and all people must be green, okay? Or whatever. The people are different materials, different chemical composition from the same basic physical law, okay? So why our universe must be any simpler than people, than birds, than, well, colors of our shirts? So in general, multicolored is generic. If you want to prove that our universe is single-colored, the burden of proof is on your shoulders, and you can't do it, okay? Now, so that's why the universe is, well, multiverse is more generic. But there is another thing. Even if you start with one-colored universe, in inflationary theory, during inflationary expansion, quantum fluctuations appear which tend to change whatever I start with. So even if you start with one colored universe, typically it becomes multicolored if it can. What I mean is that if water is just water and cannot be solid and liquid and gas, it may be only solid, then you do not ask why water is solid. It can be only solid. But if you have three options, then you cannot insist that everywhere on Earth, well, it must be only liquid. You go to the South Pole and no, it is not liquid there. So it's okay. Okay? So what happens is if you have a possibility for our universe to be realized differently, then yes, that's what I would expect generically. So generic scenario is multiverse. Now these quantum fluctuations which I mentioned, they exist everywhere. They exist just here in this room. There is something which is called uncertainty principle. When you look at tiny place and you look at it short period of time, you cannot really say that energy inside is zero. There is something quickly appearing, quickly disappearing. What inflation does, it takes these quantum fluctuations and it instantly stretches them at large distance. Once it stretches, these quantum fluctuations stretch and freeze because of this viscosity which I told you about. Then next moment, previously existing oscillating quantum fluctuations, these green ones, they freeze on the top of the previously frozen. Next moment, other fluctuations freeze on the top of those which were previously frozen, and they're all expanding to the large size. And this produces inhomogeneous universe which we see right now. Because if we would believe that the universe, that inflation works just perfectly, then it would produce the universe which do not have any galaxies. So we would over-solve the problems. We would do it too well for our own good, and we would be unable to live. So what happens? Quantum fluctuations produce these mountains in our universe. They produce something which, after everything is stretched, you have here on the top, you have energy density, or just density of matter, higher than in the minimum. This place where it's higher becomes a galaxy. Galaxies are produced from quantum fluctuations. Here there are some places where these quantum fluctuations just by chance overlap, and they push us higher. This is the value of the scalar field in different parts of the universe. They push the scalar field just by chance higher. When they push it higher, then the process of exponential expansion of the universe restarts. And these parts of the universe where they push you higher, they become new parts of the universe. New universes effectively are born. That's what I mean that the universe becomes fractal. I will tell you more about it later. But if we just look at this part, these were small perturbations, what we can do, we can just go to Florida and watch the satellite launch and check whether indeed we see something special. And if we look at the sky very, very carefully, we will see that different parts of the sky have slightly different temperature. The guy will not see it by naked eye. They really need satellites to see all of this. They see that the sky has temperature approximately 2.7 Kelvin, which is almost nothing. And then if you look to the right and to the left, you will see that in this direction it is 2.7 Kelvin plus 1,000th of a Kelvin. In this direction it is 2.7 minus 1,000th of a Kelvin. And it has interpretation. Our Earth moves with respect to the universe. And that's why you have effect of redshift, blue shift, slide. Okay? Then you subtract this 10 to the minus 3 and study it with better and better accuracy. And when you are able to measure temperature with accuracy better than approximately equal to 10 to the minus 5 of a Kelvin, which is just science fiction. But, I mean, that's just incredible. But that's what people do, okay? So they found that there are slight spots on the sky. Some of them are a little warmer. Some of them are a little colder with this accuracy of 10 to the minus 5 of a Kelvin. Okay? Now we have interpretation of what happens. Quantum fluctuations, when you stretch them, they produce galaxies and they also affect geometry of space. And as a result, you have these spots which are well, like it's like a photographic image of quantum fluctuations produced at 1 billionth of a billionth of a billionth of a second after the Big Bang, stretched so that we can see them all over the sky. And then we use all our sky as a huge photographic plate. And on this photographic plate, we see the consequences of these quantum effects which happened in the very early universe at the very, few milliseconds after when the universe was born. Okay? So then we study statistics of these, spots. How many large spots, how many small spots, and draw something which is called spectrum. So the spectrum looks like that. Here are the black things, the experimental points which were measured by different experiments. Here, green ones also. Red line is theoretical prediction of inflationary theory. So, yeah, that's pretty interesting. All of these things, they follow from inflationary theory, which at the moment when it was suggested, looked like one wonderful piece of science fiction. I've never believed that anything like that would be technologically possible to make. It's just you should never underestimate talent of your colleagues. See, I'm a theorist. For me, well, I just knew that it must be right. But I also knew that it's impossible to check. Oh, okay. Now, but these people made it. So that's just amazing. And they continue doing it, continue increasing this accuracy. So there are some predictions of inflationary cosmology, and many of them are already well confirmed experimentally. In addition, for the fact that the universe is flat, whatever, I will better run through it. I will tell you everything that I told you right now in a very, very simple ways. It will be like a break. See, I am supposed to talk about 1 hour. Okay, so we'll have like 10 minutes to go because we started 5 minutes later. And I am just making a break, okay? So here is interpretation of what I just said. This is our Earth. We're sitting out at the Earth, and we're using our universe like a huge time machine. When we're looking at our sun, we see the sun how it was approximately 8 minutes ago. When we look at distant stars, we see the stars how they were 100 years ago. When we look at distant galaxies, we may see these galaxies how they were, well, 1 billion years ago. And then when we look at this microwave background radiation, this is this tiny, tiny temperature which we are registering, we see how it was emitted approximately at the time 400,000 years after the Big Bang. Why not smaller? Because at smaller time from the Big Bang, the density of plasma in the early universe was so high that it was not transparent, so we just cannot see through. Maybe using neutrino telescopes, we would push our nose a little bit closer to the Big Bang. Maybe using gravitational waves, we will come even closer, but this was the end of the story. This is like a, circle of fire. That's the beginning of everything. That's the Big Bang story. That is something which, was true 30 years ago. And now we have this picture. This is this circle of fire, but this is the part of the universe where there was no fire yet, because fire appeared after inflation. When inflation finished, the scalar field started oscillating near its minimum. It produced particles. These particles came to a state of thermal equilibrium. After that, the universe became hot. Okay? So these circle of fire appeared after inflation. So here there was a stage, because we're using the universe as a time machine. There was a stage, the first milliseconds of the universe evolution, where it was not hot, where it was expanding exponentially. And if we decide to go even further, we'll find the places where these quantum fluctuations produces new parts of the universe ever and ever again. Our universe is a huge fractal of an enormously large size. And this fractal, you may describe it, figuratively, in terms of genetic code. If the universe had a genetic code of being red, this quantum fluctuation may make it green. if these quantum fluctuations are strong enough, and if the universe had a chance to be red, green, or whatever, just like water, if it can be only solid, we cannot do anything with it. But if it can be solid and liquid, then we may ask a question. And this is the simplest theory which was popular about 30 years ago, and it has dozen different possible vacuum states with the same energy in each of them, with totally different laws of elementary particle physics. And fluctuations during inflation can push you from one minimum to another, from one minimum to another. Inflation is over, then you open your eyes and you find yourself in this part of the universe, and this part of the universe have the same laws of physics as in our part of the universe. But some other guy opened his eyes, well, he wouldn't have eyes because laws of physics do not allow it. Well, here somebody else perhaps will open whatever he has, and we'll see different laws of physics. So each of us will be trying to explain why only this part of the universe is possible, but it's multiverse. Different people, different animals, different whatever. We're talking about life of the universe, okay? We're talking about life in the multiverse, and different types of life are possible. These are results of numerical simulations of this process, and see what happens. There are some parts of the universe which right now, as we speak, continue inflating, and they inflate with such a huge speed, and the fluctuations are so large that the colors of the universe change all the time. So laws of physics are not yet fixed here. Here, density of the universe is small, inflation done already, 10 billion years, 14 billion years of normal expansion, post-inflationary, and we are frozen, either in the red minimum or in the blue minimum. Now, if you want to go from the red to the blue, you have two problems to solve. First, the size of each of these parts is exponentially large, so it is extremely difficult to travel. Second, when you go to the border, instead of police officer, you will see a domain wall separating red from blue. And if you are, well, young and very energetic and stupid, then you go through the wall and you die. Because particles of your body cannot live in the blue universe, okay? So police officers are not necessary here. It's kind of natural selection, okay? Now, how many colors? And that is something which is really new. I mean, by really new means only 10 years old, okay? So we knew that there is such thing like string theory, and everybody said the string theory is a theory of everything, whatever. It was invented approximately in the year 85, and until the year 2003, people were saying, our universe is actually 10-dimensional. Only in 10 dimensions can we formulate string theory in a good and consistent way, or at least this is the best way to do so. Where then these extra 6 dimensions? When they're squeezed into something tiny so that you cannot move in these 10 directions. That's why our universe looks like 3-dimensional plus 1, which is 1 is time and 3 normal, well, and other 6, okay, they're squeezed into something very, very tiny, okay, except for nobody could show how exactly are they squeezing. In fact, if you try to think about it, the most natural solution, well, universe really wants to be 10-dimensional. Okay, so in string theory, it really wants to be 10-dimensional. Now, in 2003, several people at Stanford University, Kachru, Kailash, Trivedi, a person from India who came visiting us, and I was working like cosmology consultant. So we found a way how to squeeze the universe so it does not unsqueeze instantly. It will unsqueeze. It will take lots of time. Okay? So we temporarily alive in the universe which is temporarily 4-dimensional. Okay? Not for short period of time, for long, but not forever. Okay? So now we are squeezed, but in which state are we squeezing? How many options do we have? And then somebody else started counting the number of the options. And they found a number And the number in the simplest cases was given by this, 10 to the degree 500, okay? You know what is this Google? Okay. Google is 10 to the degree 100. It is not the name of the company. It's Google. It's 10 to the degree 100. That's why they take this name as something so huge they will shuffle through all of this, okay? They never thought about number like that. It is Google to, oh, okay. Anyway, many Googles. Okay. So that's how many options for our universe to exist. It may be red, it may be black, it may be whatever, it may be multicolored. This is 10 to the 500. 10 to the 500 is given because this is the first number they came with, and then they start estimating, and it came like 10 to the degree 1500, maybe 10 to the degree 5000. They're still counting. So we don't really know. The only thing that we know that it's big. Okay? Now, why is it important? We're trying to explain why these people who found acceleration of the universe, why they found acceleration of the universe which goes so slowly that until recently nobody have found it. This means that it goes slowly because energy of empty space in the universe is tiny. If it would be very large, the universe would expand extremely fast. If it would be very large and negative, the universe would collapse. Okay? So then the answer is that, of course, now we know why they have found this tiny number. Because if it would be 10 times larger than it is now, or maybe 100 times, or maybe 1,000, okay? Then it would expand so fast that the galaxies would not form. This was the famous work of Steven Weinberg of '87, and people at that time already guessed that this is something which... So we cannot live in the universe with tiny, but just a little bit larger than what people measure right now, vacuum energy. We cannot live in the state with negative energy because the universe like that will be very, very rapidly collapsing. So we will be unable to form our civilization. We will collapse in 1 millisecond. Okay? So now, therefore, we must live somewhere in between. And this may explain why these people, they found non-zero value for vacuum energy, but very, very tiny. But you can have this luxury of choosing where to live only when you have an option. If you have one universe, and whatever vacuum energy is there, that's where you live, or you do not live. You have an option to live or don't live, but you don't have an option of vacuum energy. But if you have 10 to the degree 500 different possibilities, then, yeah, just in one of these vacuums you live. Now you calculate energy in this vacuum, you find it's high, no, then it's not vacuum for me. You ask, what if I made a mistake in calculating this energy? I calculated more carefully, and whatever I calculated previously moved just a little bit and became like that. But what happens is that if you have this 10 to the 500, then in some of them, after all calculations, you find that some of them belong to this entropic bound, okay, satisfy this condition. That's why energy of the universe is so tiny. Because in non-tiny, we would not be talking about it, okay? Now, this is how the universe looks, kind of a picture. This is a picture from my old paper from '94 in Scientific American, where see, there is no Greek letters. It's only time, okay? And, but they used colors. So, this was our idea of the universe. Our universe is a big balloon. It's a big balloon, red balloon, green balloon, yellow balloon, but it's a balloon. Now, the news which are brought to us by inflation, that it's a very big balloon. And the second piece of news, that actually in some parts of this balloon, it produces other balloons. And in some parts of this other balloon, they produce other balloons forever. That's what I mean when I said that the universe is eternally existing, self-reproducing, fractal. And they used here different colors to show that laws of physics may be different in different parts of them. Different life in different parts of the universe. In some of them, it's carbon life. In some of them, it's silicon life. Guess what? We live in this part, in a Silicon Valley. Now, so here, you just stop noticing. because everybody who uses this iPhone, iPod every day, it just, you become a part of the silicon life. Now, this is what we thought about the universe, and we thought that this is a Big Bang, okay? But now, it's not a Big Bang, because maybe we are living here. We look at this part, we think this is a Big Bang, but this is not a Big Bang. This is a pretty Big Bang, but not the Big Bang. And we do not know whether there was a Big Bang or there were only this sequence of pretty Big Bangs. Probably there was some. Probably the universe started sometimes. But here we live, for example, okay? But we do not live in the first balloon. Alan Guth, who invented inflationary cosmology in '81, his model didn't quite work. I helped him to improve it. He formulated it in a way. It said that there is no such thing as a free lunch, but the universe is ultimate free lunch. That's what I said. You start with a few milligrams of matter. You get everything surrounding you. It's just free lunch. And then I was at that time at the conference in Cambridge, first conference dedicated to inflationary cosmology, and I was from Russia, and I was deeply impressed by these free lunches which they provided us with. You choose whatever you want. And after that, I formulated it like that. Now it's an eternal feast where all possible types of dishes are served. So that's the essence of all of this. Unfortunately, all of these vacua, all of these vacuum states in string theory are proven to be unstable. Yeah, it's my work. This is my contribution to this paper. These people have shown that you have many options. I have shown that all of them are bad. Okay, so all of them, they eventually decay. They can decay in different ways. You can go down to the universe with negative vacuum energy and then it rapidly collapses. Or you can go slightly, different direction, and the part of the universe become 10-dimensional. And then we cannot live in 10 dimensions. No, we cannot. Somebody else may. Okay? So you have many different ways of dying. But, I mean, beyond what people expected before, they before thought the universe grows, and then if it's closed, it collapses. Okay? So you die in fire. Now, then there was an option. The universe grows and then they continue expanding and you die in cold. Okay? So fire and cold, you have, limited imagination. Now you can die in anti-de Sitter space with negative energy collapsing, and you can die in 10-dimensional universe. You can be hit by the main wall, and you will never know that it is coming because it comes to you with a speed equal to the speed of light. At the moment when it hits you, this is the moment when you see it, and then you never report the results. So you have all of these issues, but what is important that because of eternal inflation, some parts of the universe will continue existing. So some parts of the universe will produce new babies, new us, and new SETI institutes. Is it physics or metaphysics? Can it be experimentally tested? Well, so the question, can we test the multiverse theory, or it's just, you have fine time, we had a good lunch, and then, okay. So this theory provides so far the only known explanation of numerous entropic coincidence. For example, this vacuum energy, which is extremely small. Okay, another question. You have neutron and proton. Mass of a neutron, I'm finishing in 5 minutes. Okay, so I feel myself bad because I am overseating you here. Okay, but I'm finishing soon. Okay, so mass of the neutron and mass of the proton, they almost equal to each other. If mass of the proton would be, now it's just a little bit below mass of the neutron. Neutron decays, okay? If mass of the proton would be higher, proton would decay. You would have totally different universe. We would be unable to live there, okay? So it's a coincidence with accuracy of maybe %. And we live in this universe. Why we live in this universe? If you take mass of the electron and you make it twice as larger than it is now, or twice smaller, we would be unable to live in this universe. Why is it so? Why this mass of the electron is 2,000 times smaller than mass of the proton? What is so special about it? What is so special about it is us. Okay? We would be unable to exist in the part of the universe where electron has a different mass. But in order to give this answer, you need to have these parts of the universe where electrons have a chance to have a different mass. So multiverse is, as of now, the only existing explanation of experimental facts. So when people say we cannot travel that far and therefore the universe, well, multiverse theory cannot be tested, it's already tested experimentally by our own existence. You may say, but this is nevertheless not something like that. What we want is to make a prediction and then check it experimentally. And what I answer to that, this is not how American court system works. People, for example, the person killed his wife. They do not repeat the experiment. They do not give him a new wife and a knife, etc. What they do, they use the method suggested by this philosopher. Okay? So they just try to eliminate impossible options. And once they eliminate it, either the guy goes free, or the guy goes dead, or a mistake. Sorry. Okay. So everything is possible. But it is not necessary to make a repeated experiment, check what is going to happen with the universe if it cooked up differently. It's possible if what we have provides the only explanation of the facts that we see, it's already something. So now I will give you, in these last 3 slides, I will give you explanation of something which is totally unexplainable. Okay, so, why it does not show me, computer, okay, the silicon brains. So I will tell you what was supposed to be there, but for whatever reason the letters became white, okay? White on white you cannot see. So Einstein said something like that, that what I want to explain is whether God has any options in creating our universe and why it was produced this particular way. Eugen Wigner, who was famous physicist, he said a thing which was kind of almost unrelated at the first glance, but it sounded approximately like that. The most incomprehensible thing about, this was Einstein. The most incomprehensible thing about universe, said Einstein, is that it is comprehensible. Actually, I've heard it first at Bloomberg. At Bloomberg, there was some interview of some famous woman physicist, and after she explained everything about multidimensional universe and stuff, and this was the end of the interview, this Charles Rose, smart, intelligent person, finished it with the words of Albert Einstein. But the most incomprehensible thing about the universe is that it is comprehensible. And she didn't know what to answer. Yes, Einstein beaten all of us, because if physicists cannot explain even why the universe is comprehensible, so what do they do with their theory? They cannot explain the first thing about our world, why they can think. Okay? Now, Wigner formulated it differently in terms of mathematics. He said that and let's see, the incomprehensible efficiency of mathematics. Why mathematics is so efficient? It could be that whatever you do, 2 plus 2, at some moment it becomes 5, at some moment 8, at some moment 4. You cannot make predictions. For whatever reason, mathematical laws in our universe work perfectly well. And he was half physicist, half mathematician. And as a mathematician, he was challenged by why mathematics works. So Einstein, like a physicist, was challenged by physics works. Wigner was challenged by mathematics works, and I decided to check what the new generation of mathematicians did, and I've read what a Russian famous mathematician Golfand said, and he said, the only thing that is more incomprehensible than efficiency of mathematics in physics is its total inefficiency in biology. So all of them are complaining about something. So now let's try to understand why physics and mathematics are so efficient. So the reason why they were puzzled by efficiency in physics and mathematics is very simple. If the universe is everywhere the same, and generic universe may be a total mess, then in a total mess you cannot make any predictions. Your mathematics and physics will be totally useless. For example, some parts of the universe cannot produce any observers at all. Then these parts of the universe would be nobody who would contemplate about what is mathematics. There will be nobody living there. There are some parts of the universe now, and that's serious, where density is so large that fluctuations are so, incredibly swift and strong that once you try to record anything, next millisecond this recording is destroyed. So you cannot make any predictions because all results of your calculations, your predictions, instantly destroyed. These are the parts of the universe where mathematics and physics is inefficient. So now what we are saying that we can live only in the parts of the universe where this natural selection is possible, where predictions are possible, like prediction that I'm going to finish this talk in 2 minutes, okay? Like a prediction, each of us will try to predict stock market. Does not work, so you predict something else. Okay, so what? We need to make predictions at every step of our life. If we would be in the parts of the universe where predictions is impossible, we would not be there. I mean, somebody else can, but not physicists and not mathematicians. So that's why physicists and mathematicians can live only in the parts of the universe where physics and mathematics are possible. Nothing deep about it, it's just trivial. And so we live in the parts of the universe where our own institute, which is Stanford Institute of Theoretical Physics, may exist, and also SETI. And okay, so how it looks. This is the picture of the universe which, well, I used before. So now, in general, there are some parts of the universe where we cannot live, and there are some parts of the universe where physicists like Einstein can live. There are no miracle. So Einstein can live in the universe where Einstein can ask a question, why the universe is comprehensible. So now we know what to answer at Bloomberg if we were ever asked. Thank you.
Thank you to our speaker for an excellent and relatively concise summary of a very interesting topic. Let's take a few questions.
Hi, yes. It wasn't completely clear to me your motivation for multiverse versus the Entropic principle. At SETI, we have a version of the Entropic principle which is habitable. It's the same idea. You try to narrow down your space. So in your situation, it's not clear to me that just the Entropic principle, you seem to be arguing against it and then for it in your talk.
Right.
Do you care to comment?
So Entropic principle without inflation doesn't explain why it was necessary to make the universe uniform on the scale comparable to the total horizon. Inflation does it. If it is good in the vicinity of solar system, it's good everywhere. But this by itself would not explain why Entropic principle work at all, because if you have one option only, like we had in Russia, you go to vote, and they give you, well, vote, and there is a name written there, and just one name, okay? So then, whatever, vote or don't vote, it doesn't work. So what string theory does, it gives you 10 to the 500 different options. So now you have a possibility to implement Entropic principle with help of inflation, which makes every single part of the world so large that you can really either live or not live there. So everything then becomes like a consistent theory.
All have 10 dimensions, all the universes?
No. Well, internally 10 dimensions, but 6 of them are compactified.
All 10. It's all string theory.
That's a very good point. What I'm studying right now, I'm studying something very conservative. Okay? I am assuming that there is one theory which explains everything. Okay? If this is so, like water can be liquid, solid, or gas, okay? Even if everything is described by string theory, the goal of string theorists previously was to realize the dream of Einstein and to find only one theory which explains everything, the only one, the best. Now string theorists see that actually they need this multiplicity, because this multiplicity allows them to explain, well, many properties of our world. They are quite happy, okay, not very happy, but relatively happy about this multiplicity of different outcomes.
Hello, over here. Hi. The large-scale structure of the visible universe, if it's just quantum fluctuation that gave rise to galaxies and associated clumps of dark matter, I would expect to see a galaxy here, a galaxy there, whatever. But we see these large filaments of a certain size and these sheets of a certain size. And I'm wondering if the specificity of those sizes and shapes has something to say about the overall size of the universe beyond the visible and where we might be in this fractal pattern.
Okay. So first of all, if we assume that the spectrum of perturbations, as it is usually the case in inflationary theory, the spectrum of perturbations is simplest. It just does not depend on any scale. A little bit. There is a little bit of dependence on the scale. So the amplitude of perturbations on the scale of 1 megaparsec and a 10 megaparsec and 100 megaparsec, approximately the same. These, cosmologists take this assumption. They put in their computer simulations. They get this structure with shells and voids and everything. They get it as a result of numerical evolution. Okay? So the first thing. But the fact that you have this tiny dependence on the scale is a very important thing. It's, usually, not in every theory, but in many, the amplitude of perturbation slightly grows when the scale grows. Okay? So that is what we see right now experimentally using WMAP satellite. We see that the spectrum is not flat. The flat spectrum is excluded by experimental data by more than 3 sigma. Okay, so it's practically excluded. Now, this slight growth of the amplitude actually means that a very, very large distance, this amplitude, or suggests, okay, becomes so large that the universe will have this fractal shape. So depending on the slope, how the spectrum grows, you will expect the size of the fractal is either smaller or larger. So, but this relation is not definite. It's only suggestive.
If we adopt a notion of the universal wave function in average senses, the wave function that describes the state of the entire universe, yes. So does it make sense to consider it as for multiverse, or it's only for our universe in narrow sense?
Average interpretation of quantum mechanics, this many-world interpretation of quantum mechanics, is something which was not loved at all, to say the least, by many people a long time ago, and which becomes more loved right now. Okay? But this is just an interpretation of quantum mechanics, which would work perfectly well whether we have inflation or don't have inflation, whether we have these 10 to the 500 different vacuum states in string theory or not. So when we are talking about this multi-universe multi-world interpretation of quantum mechanics by Everett, it's a very interesting thing, but it may describe, for example, all universes where you still have electromagnetic interactions and that's it. You don't have any different colors there. Different colors is something additional which added to Everett interpretation by study of inflation and string theory. So Everett interpretation is a very interesting thing. Whether it is a total story, I'm not totally sure. People who study interpretation of quantum mechanics I have a feeling, but that's my personal feeling, that they're missing something. They're missing the role of our own consciousness in the place. If we would like to consider the general theory of the universe, we must add a person there in some deeper sense than what we're doing right now. And maybe this will bring some, more profound interpretation of quantum mechanics. But this is not what I'm doing right now. As I said, we're doing a small thing yet. Small thing already quite interesting.
But this is not only about Everett's multiverse theory, but about the possibility of existing the entangled particles in two different universes in this multiverse. Is it possible theoretically?
The identical particles?
No, entangled particles. So the particles that have correlated in quantum sense.
Oh, it is possible, and
Is it possible to have the two particles that would be entangled in this sense, but existing in this different...
The correlation between particles, maybe we're talking about two specific things for the audience, but the quantum correlations, they are possible even without any inflation. People are doing teleportation right now from one island in Italy to another. It's difficult stuff, but the quantum correlations, they're quite a real thing.
And I'm going to cut off the questioning here just in the interest of time, but let's thank our speaker one more time.